right? Again, what makes it an exponential function is that our variable is an exponent. This is kind of our most basic exponential function. There's just a number that is our base, our variable is an exponent. We can do all sorts of transformations to this if we want. We could have a multiplier out front to cause like a vertical stretch. We could have, some reflections by putting a negative in front of the exponent here in front of the x. We could shift it to the right, to the left, up, down, whatever. But for the most part with exponential functions, we're just going to be thinking a lot about the most basic version of it. So there you go. Here's some examples of some graphs of exponential functions. These are all exponential growth with a few different bases, base 7, base 4, base 2. Obviously, you can sort of see that the higher that base value is, the more sort of vertical, the faster it grows, even though all of them grow pretty quickly, right? Even 2 to the x, which is a relatively small base, approaches going vertical pretty quickly, whereas 7, it's even faster than that. And they all look like they have an asymptote along the x-axis, and they do. All of these exponential functions are going to have an asymptote along the x-axis. Obviously, if we shift the graph up or down, we would move that asymptote along with it. But again, we're mostly going to be looking at functions that are pretty simple like this. Some things to remember, a does have to be greater than 0. We can't have any negative bases because some weird stuff happens when we're dealing with negative numbers raised to exponent powers. Some really weird stuff. Like for instance, if you had a negative base of -2 and you try to raise it to the 1/2 power, you hopefully remember that is the same thing as doing the square root of -2, which is not defined. That's not a real number. So negative bases cause some issues. Some of them are like this, but also negative exponents just to normal powers, like, right, -2 to the 3rd power is -8, but -2 to the 2nd power is positive, it's 4. So negative bases would oscillate and they would cause errors like this, all kinds of weird stuff. So we can't have any negative bases. Exponents are fine. Exponents can be any number we want. We can have negative exponents, right? Remember, if we have a negative exponent, what that means is 1 over the positive exponent. So 1 over 9 in this case. So negative exponents are fine, or even an exponent of 0 is okay. Anything to the 0 power is always 1. These are some basic exponent rules that I hope you remember. We'll be making use of them quite a lot here. So if you're having trouble with some of those ideas, hopefully you are kind of picking it up as we're talking. So anyway, the exponent, the domain, the x values can be anything we want, all real numbers. All right. So in general, we have kind of 2 different types of exponential functions, some of them that represent exponential growth, meaning it's increasing. So here's a really simple exponential growth graph, 2 to the x. What makes us know we're dealing with exponential growth is that our a value, our base, is greater than 1. Anything greater than 1 is going to cause an increase as the x values increase, right? 3 to the 1st is smaller than 3 to the 2nd, 3 to the 3rd, right? These things are increasing as we increase the exponent power. Exponential decay can happen in a couple different ways. The most common way is this top one right here, where our a value is between 0 and 1. Our base is between 0 and 1. So it's usually some sort of a fraction like 1/3 or 1/2, or it could even be a decimal like 0.8 to the x, right? Anything like that is going to cause decay, because as you raise fractions or decimals that are between 0 and 1 to an exponent power, the numbers actually get smaller and smaller as the exponents get bigger and bigger. So it's causing that decrease that's happening. Now, another way that exponential functions are sometimes written to show decay are keeping an a value greater than 1, but putting a negative in front of the x. Remember what that's really doing, that's a transformation. That's causing a reflection across the y-axis. So if we take a regular exponential growth graph and reflect it over the y-axis, you turn it into exponential decay. It's no longer increasing. Once we reflect it, it looks like this, right? And now it's decreasing. So that's another way we could write exponential decay. That's not as common. Again, the most common way is with a base between 0 and 1. Now, again, our base can't be a negative, can't be 0, and it can't be 1 either. 1 is totally uninteresting. If we had an exponential function of 1 to the x, that would be totally uninteresting because 1 to any power will always equal 1. So we would end up having just a horizontal line. It wouldn't be a growth or decay graph at all. All right, again, hopefully a lot of this stuff is, you're sort of remembering it. Again, the idea was review for the first day or two here and then new stuff. All right, so here's a real world example of an exponential growth formula. So it's called the compound interest formula. So when you invest money in like a CD or something like this that does compound interest, you can calculate the value of your investment using this formula. So all of these are what the different variables or parameters stand for. So A is the final amount or final value of the investment after some amount of time. P is the principal investment. So it's how much you put in the beginning. R is the interest rate. That is always as a decimal. So if you had say a 2.5% interest rate, you would need to write that as a decimal, 0.025. You divide this by 100 to get that. Always write it as a decimal. N, this one's a weird one that people a lot of times don't understand unless they've done some sort of like investment account stuff. It's the number of times that the interest is applied over a period of over some sort of time period. Usually that time period is years. So a lot of times when you're investing in some sort of thing like this, it'll say, oh, you know, your investment is going to compound monthly. So it will calculate your interest every month rather than just once per year. That doesn't mean you get 2.5% of your interest every month. It means that you get 1/12 of your interest every month, and then it recalculates it. And usually the more times that it compounds, the better off you are. You're going to get more money. And then T is the time period. So how long are you actually investing in something? So are you investing for 6 years, 3 years, a month, whatever? All right. Investing can be kind of boring, but this is an actual example that does get used. So there we go. So let's actually just use this formula. So here we go. We're going to calculate the value of an investment of $500. So that is our P, our principal investment, at 2.25% interest. So that is our R, which would be 0.0225. Compounded quarterly, which means 4 times per year. So that means our N is 4. Over 12 years, that's our T. That's the total time of the investment. So we have everything we need. We have the P, the R, the N, the T. We got it all. We can just plug it in the formula. So A is going to equal 500. That's our principal investment. 1 plus 0.0225 over 4 to the N times T. So 4 times 12. I'm just going to use a calculator for this. Again, there's no reason to do this calculation by hand. So there we go. 1 plus 0.0. And 4 times 12 would be 48. So I'll just put 48 there. Okay. So here is my calculations. Is that backwards on the screen? Why is that? No, that's backwards for me. You guys see it normally. So after those 12 years, compounded quarterly, the $500 investment would turn into $654.49. We round that up. So our answer here, 654.49. This is pretty uninteresting in terms of like an actual calculation. It's just kind of a plug and chug sort of idea. We're going to come back to this when we can do some more interesting things with it, where we can solve for stuff rather than just straight calculate. So let's do one more calculation. So an investment of 3,500, that is our P, at an interest rate of 3.125, so that's 0.03125, compounded semi-annually, which is 2 times per year, over 28 years, so 2 times 28. Again, pretty much just a straight plug and chug idea, but I wanted to do another one just for 2 times 28 is 56, so to the 56th power. Okay, so doing that, $8,339.45. 8,339.45. Again, we're just kind of doing this as a straight evaluating, but this is an exponential function. If we knew the investment, the interest rate, if we knew everything but one of our parameters here, one of our variables, then we could create it as a function, right? If we knew the interest rate, the number of times it compounded, and the amount of time we were willing to invest, then we could do a function of, oh, how much should we invest here, and figure out kind of, that way, or other things. Generally, if you want to write as a function, you need to know all but one of our variables, right? That way we can write as a function of that variable. Let me go ahead and clear this. What about a question like this? So this kind of gets to a more interesting idea. So we said, how many years? So in this case, we do not know the time. We do not know how long the investment is going to be, but we know everything else. We know the principal investment is $1,500. We know the interest rate is 4.5%, so 0.045. We know that it's compounded monthly, which means 12 times a year, so 12. And we don't know the time, so this is going to be 12 times t. We do know how much the investment is going to be worth at the end. We want it to be worth $1 million. So what do we need to do here? There are a few ways to approach this problem. We could start guessing. We could just make some guesses for t. We could say, I don't know, maybe it's 60 years. I don't know. Just throwing out a number there. So I'm just gonna do a quick calculation where I'm just kind of estimating it. Obviously, that's not ideal. 12 times 6. Oh, forgot to put that as the next one in. 12 times 60. Okay, so 12 times 60 didn't work out. That's nowhere near a million. That's $22,000. That's not even close. So 60 years, not even right. So after 60 years, I mean, we're starting to talk about that's not even viable. Let's go up to 100 years just for curiosity's sake. Okay. 100 years, still not even there. So looks like this is not even really a viable investment. I was only at 100,000, but just in the interest of solving the problem, let's keep going. Let's say 1,000 years. Okay, that number is too big. I'm not even gonna put that up there. Let's go 300 years. All right, 300 years is sort of close, but it's also too big. So kind of narrowing down on it, but obviously you can see that guessing is not a great way to do this. The question would be, this is just an equation with a single variable. Why can't we just solve for that variable? Well, we could try. We could divide both sides by 1,500. So that would be 1 million divided by 1500. Okay, so that's actually $666.67. 1 plus 0.045 to the 12 to the 12t. But now we get to this situation where, how do I solve for this variable? Now you guys might remember how to solve for this variable right now. What we need to do is actually use what are called logarithms. The way that we solve for a variable that's in an exponent place is by using logarithms. We haven't done that yet, so for now, we're going to say we don't really know the answer to this question. We'll save it for later. All right, here's another real-world example of an exponential function. So again, it's an exponential function because our main variable, time in this case, is an exponent. This is what's called the radioactive decay or the half-life formula. So radioactive molecules have an exponential decay. They follow an exponential decay over a certain period of time. So N0 is the initial quantity of our substance. T sub 1/2 is the half-life. So how many years does it take for half of that radioactive substance to decay away? And then we have a formula. So let's actually use this real quick. All right, so here's an example. The half-life of carbon is 5,000, carbon-14, that's a specific isotope that is radioactive, has a half-life of 5,730 years. So you might have heard of carbon dating, where scientists can use the amount of radioactive carbon that's present in something to approximate the age. So they do that based on knowing the half-life of this particular thing. So they could use a formula similar to this to date. This particular isotope, I believe, is used for human things because 5,730 years is a relatively appropriate time for human dating. They wouldn't use that for like dinosaurs or something because that's not an appropriate time frame. When we're talking about dinosaurs, we're talking what, 75 million years or something. So carbon-14 is useless for that. They'd have to use some other isotope that has a much longer half-life, but we're going to use it for this one. So if we begin with approximately 12,000 atoms, that is our N sub 0, our initial amount of carbon-14, how many atoms will be present after 2,000 years? That is our time that we're dealing with. And we already know this is our half-life, our T sub 1/2. So we can figure this out. We get 2,000 is our initial amount times 1/2 to the 2,000, that's our time, over 5,730 years, our half-life. So we can, again, do a quick calculation of this and see how much would be left after 2,000 years. I'll do a quick calculation with this. 2,000 over 5730, and there we go. That's our number, 1,570. So I'll write it out.
Mr. Michener?
Yep.
Shouldn't N initial be 12,000 atoms?
Oh man, you're right. Well, I messed that up a little bit, so let's do that. Let's type the right number in. Got mixed up, had two 2,000s in there. Okay, so yes, thank you. That is 9,421, approximately. Now, that's not that interesting. I mean, that is about 3/4, right? That's about 3/4 of it left after that amount of time, 3/4 of the original. But the idea here, this isn't the way that like a scientist in the field would use this. Obviously, they use tables, they use other things, but this isn't the way that they would use this formula in the field. They wouldn't just plug in the number and go with it that way. Because when you're dating something, the only thing you can measure is what is currently present. So what you would be measuring is the output of this function. And you would know the time. You would have to solve for what the original amount was and the time. You have to sort of make some estimations here. So, you know, this is an example of using an exponential function, though it's not quite the way they would be used. You'd have to use it to sort of solve for something. Obviously, if they knew what the object was, if it was like a, you know, we're talking about human objects, if it was some clothing or something, they could estimate the original amount that would have been present, thus allowing them to solve for time, right? So the use of these formulas are more interesting when we're solving for them rather than substituting values in and calculating. And in order to solve for them, we need to know stuff about logarithms. So that's going to be kind of the next idea that we'll get into. Before we do that, though, there's a really important thing called the natural base, E. E is called a couple different things. It's called Euler's number or Euler. That's why it's E. It's also called the natural number. E just shows up in a lot of places unexpectedly. So it is an irrational number right here. 2.71828. It's irrational, so it's non-repeating. It just keeps going on forever. And a lot of times it's useful for us to use E as the base for an exponential function or a logarithmic function because it works better than some other numbers. Why? That's a little more complicated to get into. We're just going to say that it does. So one of the places that E shows up, and this could sort of bring us back to some things we've talked about recently, is a particular limit. You might notice in here, this thing kind of looks like the compound interest formula, sort of, right? We're missing an R and an N and an NT, right? But like it's mostly the same as the compound interest formula. And we'll kind of come back to that in a second. But basically what we're saying is this particular function, which is similar to the compound interest function, if we go out to infinity, which we haven't talked about limits as x approaches infinity. But if we go to sufficiently large values of x, then this function starts to get close to E. And we can look at it graphically. We don't really have the tools right this second other than graphically to show this. But if we pick some really big numbers for x, we can never pick infinity specifically because that's not a number. But if we pick some really big numbers like 1,000,000 or something, we can see that it's pretty close to E. And we'll do that. We'll actually take a look at this on Desmos. So let me pull that up. Clear what I have on the screen, perhaps. So our function is going to be 1 plus 1 over x to the x. It's a weird graph, and a lot of weird stuff happens with negative numbers here. That's why we get all this kind of jumping around nonsense, because negative numbers as on the inside here can cause some issues until we get to bigger things. But what we're really concerned about as we go arbitrarily far out, it sort of looks like it's flatlining at a particular value, and you can see that E is 2.72 about if we round it up. You can see that it's pretty close. I'm not very big. These aren't very big numbers yet. I mean, we're only in the 40s. But you can see that it is sort of flattening out. It's not growing very much, and the output values are relatively close. So let's zoom like way out till we start to get some really big numbers here. All right, 500. At 500, we're already pretty close. Remember, E is 2.71828. Keeps going from there, but 2.7818. And I could keep zooming out to make this like really big. Now we're at like 20,000. Now we're really close, and it's just almost flat. So it appears as though there is a horizontal asymptote at y equals e, which is our number here. And we can, as we zoom back in, we can sort of see that asymptote behavior happening, right? Ooh, that's hard to tell. Center the graph. You can see that the graph gets closer and closer and closer and closer to E the farther we go out until it basically merges with E. So we can say that the limit of this function as we go to infinity, as we get arbitrarily large, is E. It's just a weird thing that happens. It's a fairly important result for us for a lot of different ways, but again, we're not going to go too much into it right now. It's just kind of an interesting oddity. And that's why we assigned this special value E as a number, because it shows up. Just like the same way we assign pi to a particular value, because it's a mathematical constant that shows up, particularly regarding pi in circles. So we use E. E is a base for some of our exponential functions. One of the places that we do that is in this particular formula right here. The compound interest formula, we use a base of E. The difference between continuous compound interest, which this is, and this one is, if you start increasing the number of times that you compound interest, so we were dealing with compounding it twice a year or 4 times a year or 12 times a year, as that number gets large enough, this formula, particularly that one part of it that looks like the thing we were just talking about, the 1 plus 1 over x to the x, this part of our formula basically goes to E. It's a little bit more complicated algebraically to show that, but as the number of times we compound our interest gets sufficiently big enough, the limit of it is E, because we could algebraically show that this is the same thing as 1 plus 1 over x to the x, which we do know does approach E. So essentially this part turns into E, and we end up with this formula right here. Actually, it turns into E to the R, but that's a different situation, E to the R. But yeah, so there we go. We get our formula for compound interest and our continuous compound interest involving E. Some investments calculate compound interest continuously, and that's what it means to use this formula right here. This will be our last thing. Let's compare a compound interest calculation with a regular interest calculation and just show the difference. So we're going to do a compound interest example and then the same investment, but only quarterly, and just show what the actual monetary difference would be. So in this one, we're investing 8,000 at 3.625, so that's 0.03625 compounded. Oh, I'm sorry, this one was continuously. So I'm going to do the one that's quarterly first. So quarterly for 6 years, so 4 times 6. So this one was supposed to be the second example. That's okay, I'll just move it. So we do this calculation. This is our standard interest formula. 0.03625 over 4. 4 times 6 is 24. So there we go. So I got that this calculation was around $9,933. and 99 cents. Let's do so this is actually a simpler formula. It's a lot less to it. So let's do the continuous interest. 8,000 e to the 0.03625 times 6. So 8,000 times e to the 0.03625 times 6. So doing my calculation with E with that formula, I got $9,943. Difference is minimal, but $10 over 6 years. So the difference between compounding continuously and quarterly is not substantial, but there is a difference, right? The more times you compound, the more it'll be. So if we compared quarterly to monthly to bi-monthly, we would start getting closer and closer to this, because the more times we compound it, the more we get closer to that limit, which is our continuous compound interest formula. Again, this is just an application of it. We're going to talk about some more interesting solving stuff next. It's 9:40 or 11:43, so that's the end. No new assignment for this week. Just make sure you try to finish that chapter 2 test. Okay. See you guys tomorrow again.